2.3 atoms and molecules. We're going to start with the very basic definitions of elements and compounds. So the pure substances are divided into two categories, elements, and elements are the substances which cannot be further chemically broken down into simpler substances. And compounds are pure substances that are made up of two or more elements which are chemically combined together. These are the most basic definitions. You actually already know these definitions from previous classes as well. A few pieces of information that are worth reading to all of this is that the entire universe is made up of many elements, more than 100 elements, of course, but universe is made up of hydrogen 92% and helium 77%. So 99% of the universe is made up of two gases alone, right? There are a total of 94 elements out of 118 on the periodic table that are found naturally in the Earth's crust. For example, if we talk about human body, then 65% oxygen, and oxygen actually tops among all the elements with the highest percentage. Then comes carbon, hydrogen, nitrogen, calcium, and so on. So what should you know about all of this is that hydrogen is the most abundant element in the universe, and oxygen is the most abundant element in the human body. All right. Chemical reactions and physical changes. Now they are going to simply discuss about decomposition, where a chemical reaction where a compound breaks down to form two or more substances. They're going to take one example, and that example belongs to copper to carbonate, when we heat, the green colored copper to carbonate is converted into two separate compounds. Actually, it's broken down into copper to oxide, which is black in color, and it gives away the carbon dioxide gas, right? And then there is synthesis. Synthesis usually discusses the formation of magnesium oxide ash from magnesium by burning the magnesium ribbon. This is one of the most common experiments that we start off with in lab. I hope you have done this experiment in lab yourself. Instead, I'm forgetting, you might not be going to the lab due to Corona and all of that, right?
Yes.
Okay. So this might be the first experiment and the easiest one you do if you get a chance to go to the lab. Now, when we talk about a chemical reaction, this big portion is very important. Chemical reaction is usually defined by its characteristics. It forms, gives away new chemical substances. The process is not easily reversed, and energy is often given out. Energy might be taken in during a chemical reaction, but it's the word often which keeps the whole sentence safe for us. Because most of the time, yeah, the chemical change, the uh, heat change is about the heat energy being given out. Okay,
So,
right? G,
your screen is stuck on
stuck on what? Okay, I've
chemical.
started changing it now. Does it change for you too?
Yes, now it's fine.
Okay, good, good, great. So I'm going to come to the next page, and this page is important in terms of its table on the page. This table has been manipulated into many questions, and what I'm going to do is that I am going to talk about this table with the headings given on the top of the table when a mixture forms or when a compound forms. I'm also going to give them separate headings, and I'm going to call the when a mixture form as a chemical change, and this one, sorry, physical change, my bad, and when a compound form as a chemical change. All right. I want you to go with the same headings because we're going to use and discuss these words at the start of chapter number 4. We then relate this very table to chapter number 4. But I hope you understand when a mixture forms, it's just a physical change because you have mixed a few things without going through a chemical reaction. And when it is a compound formation, it's actually a chemical change going on. Let's go through the different properties of the process so that we actually understand what these changes are about. So when a mixture is formed, the substances are simply mixed together and there is no chemical reaction between them. But for a chemical reaction or for the formation of a compound, the substances need to chemically react together to form a new compound. And this can always be written in a chemical equation. Moving on, for a physical change for a mixture to be formed, the composition of mixture can be varied. whereas the composition of new compound always remains the same. Let's help with some very basic examples that we can give for physical and chemical change over here. Now, the composition of the mixture can be varied. I take usually the example of fruit salad for this purpose. Now, fruit salads are commonly things that we love at home. We also call them fruit chaat, the typical Pakistani dish. Now, when it comes to the formation or to make fruit salad, and whenever children are asked by their parents to do that, what we usually observe is that they fill up the salad with their favorite fruits and they try to put in as less as possible for the fruits that they dislike. For example, if you like mangoes and you like apples and let's say you like bananas, but at the same time you don't like grapes at all. So we'd see that when you're going to form a fruit salad, you're going to fill up the entire combination or composition with mangoes and bananas and apples, and you'll try to put as less grapes as possible. Just giving a simple example so that you can understand that the composition can be varied, whatever we like. Let's say some other sibling loves grapes, they are going to put in more grapes than as compared to the fruit that there is like. Get my point?
Yes, sir.
Good. So the composition of the new compound is always the same. For example, if we are forming water from the combination of hydrogen plus oxygen, and whenever this chemical reaction occurs, the water has exact fixed same combination or composition. It has two atoms of hydrogen and one of oxygen, or in terms of mass, they have the same mass every single time for water, and the formula or this combination can never be changed. If you change it to like H2O2, it's not water anymore. If you change it to HO, it's not water anymore. The water would always have this composition. The composition in case of a compound formed from a chemical reaction would always be the same. Moving on, the properties of substances present remain the same. For example, if you add sugar to water, it would sweeten up the water. If you add it to a dessert, it would sweeten up the dessert. If you add to a fruit salad, it would sweeten up the fruit salad. So actually the properties of the substances that are being added to a mixture, simply added to a mixture and not chemically reacted, will remain the same. However, the properties of new compound are very different than those of elements in it. For example, hydrogen gas can be burnt explosively, as we studied back in chapter number 1. Oxygen is the gas that is required for burning. If you don't have enough oxygen, it won't burn. In the absence of oxygen, things usually don't burn. Water, on the other hand, is usually something that is used to extinguish fires. So, hydrogen can create a big fire as it is very explosive. Oxygen helps with that burning. But when they do two of these combine to form water, that actually helps extinguish a fire. So the properties can be very different from the elements. I hope you get the point, right?
Yes, sir.
Moving on, the substances of the mixture can be separated by simple physical means, such as you can separate an insoluble solid from a whole solution thing with the help of filtration, or you can separate the liquid from a soluble solution with the help of distillation, or you can actually separate anything that has magnetic attraction, for example, iron, or for example, nickel, or for example, cobalt. Elements like these can be separated from the rest of the rubbish with the help of magnetic attraction, as we studied about junkyards. So the compound cannot easily be separated into elements. So you cannot convert water back into hydrogen and oxygen easily. Yeah, we're not saying this is impossible. That isn't true, but it's not easy either. Makes sense?
Yes, sir.
So all of these are what? These are about the properties of chemical changes. And all of these are what? These are about the properties of physical changes. Hence those headings. So I'm going to clear these up and we're going to move forward. So At the start of the discussion in this very idea of atoms and molecules, the word atom was given by Democritus. Democritus thought that the atom is so small that it cannot be further subdivided. So he actually came up with the word atomos, which meant indivisible. Atomos is actually the word which means we cannot further divide it. We call it indivisible. Another term that we commonly use for atomos is unsplittable, something that you cannot split any further. So the word atoms comes from that. It was first discussed and revived by Dalton. Dalton actually gave a theory, Dalton atomic model, and that atomic model has been summarized by you for you in 4 points. Let's go through those. Now, a pure element is composed of atoms. The atoms of each element are different in size and mass from other elements. The atoms are the smallest particles that can take part in a chemical reaction. And lastly, atoms of different elements can combine to form molecules of a compound. Sorry, what are you saying?
What is glitching?
My voice is breaking,
Glitching.
glitching with your voice.
I say.
Actually, at my end, the whole internet is working fine. Can it be a problem at your end? Since every time I have a problem at my end, I usually get a notification about the instability of the internet.
Then should I rejoin? Maybe then it will be fine.
Yes, we can always do that. So I was talking about the third point. Atoms are the smallest particles that can take part in a chemical reaction. And finally, the fourth point, the last point, atoms of different elements actually combine to make molecules of a compound. I guess you're already familiar with all these points and they are easy. But if you still have a problem with any, let me know. Or should we move further ahead? Okay, great. Moving on. Dalton was actually observing the random motion of dust particles in suspension of water or smoke particles in air, which is also known as Brownian motion. And we're going to discuss Brownian motion a little later in the same chapter. Now, Dalton's theory was one of the major theories that brought a change, and then we started seeing atom as something that we need to be more aware about. So we slowly started combining all the elements into one table and we started a chemical language for that. Dalton even suggested a few symbols for that. And the next page, you would see elements and their symbols. There are many elements considered over here. You're soon going to be familiar with them and you'll memorize most of them. So I don't want you to go ahead and cram it, but as soon as you see it, you get the idea that how symbols are done. But I mean to put forward a few points and then keep them in mind. Number one, the element can be named or symbolized by any factor. It can be a Latin name, it can be a Greek name, it can be a dedication to the scientist, it can be name of the city, it can be anything like that. All right. For example, copper has the Latin name cuprum and hence its symbol. Okay. Remember, whenever you're writing the symbol, the first letter is always capital and the subsequent letters are always small. Any other combination, like all the letter capitals or all smalls, or first small and the rest capitals, are not accepted as symbols. There is only one way to write a symbol, and you should make sure that you follow that one way. Make sense?
Yes, sir.
Good, great. This completes the symbol portion for us. On the previous page, we had a heading about the kinetic model of matter. Kinetic model of matter actually explains all three states with respect to a few more points that we're going to discuss over here. You'd see a big pink portion with four separate points that we're going to discuss. Along with that, figure 2.23 is going to help us with kinetic model. Remember, kinetic model is one of the most important things in chapter number 1 So make sure that you remember their points, you can understand them well, and then you can reproduce them in different scenarios and portions. Starting off with the first point. All matter is made up of very small particles. Different substances contain different types of particles. It may be composed of atoms. It may be composed of atoms. It may be composed of molecules or such. Let's come to point number two. The particles are moving all the time. The higher the temperature, the higher the average energy or the movement speed of the particles. In a gas, the faster the particles are moving, the higher the temperature. I hope this point is clear. Actually, what this point tries to say is that temperature and kinetic energy are directly proportional. Higher the temperature, higher the movement speed. Lower the temperature, lower will be the speed of movement. So the freedom of movement and arrangement of particles is different for all three states of matter that we're going to discuss in this figure 2.23. Last point before we move up to the figure, the pressure of a gas is produced by the atoms or molecules hitting the walls of the container or the lid of the container. The more often the particles collide with the wall, the greater the pressure of the gas is. So let's consider all of them by considering some specific diagrams from them. Starting off with gas. If taking the example of gas, which is usually enclosed in a bulb, you'd notice a very few atoms of particles and they are far away from one another. So the particles in the gas are arranged totally irregularly. They spread very far apart as compared to solids and liquids, and they are able to move randomly. On heating the particles, the liquid expands into gases. In the liquid, some particles have enough energy to escape from the surface. We call it evaporation. As the temperature rises, more particles have enough energy to escape the surface, and evaporation is faster at higher temperatures. At the boiling point, the particles have enough energy to break the forces attracting them. So what happens, the particles of liquid move very fast, separate from one another, go away from one another, and we say the liquid boiled and converted into a gas, which we just studied. Which brings us to study the liquid. The liquid particles are closely packed together, but still there is still an irregular arrangement, and they are able to move around or move past another. Sometimes we also use the phrase they are able to slide past one another, hence which gives the liquid the capability to flow. So when we discuss the conversion about solid to liquid, I mean melting. So whenever the temperature is raised, the particles gain energy and they vibrate more strongly with a fierce manner. The particles then try to occupy more space. This causes the liquid to expand. Eventually, the particles have enough energy to break the forces holding the lattice together, and they can now move around, move past one another, or slide past one another. We say the solid melted and became a liquid. Finally, it's time to discuss the solid particles. Solid particles are packed close together. They also have a regular arrangement. This arrangement is sometimes known as a lattice. Don't worry, I'm going to define the lattice word over here, but a little later. The last point in the solid says that they are not able to move freely, but they simply vibrate in their fixed position. They will never be able to move from their fixed position, but yeah, they can vibrate. So, what is a lattice? And don't forget that this entire definition is important. So, mark this, and this can be written in the paper for the definition. And let me tell you, in past 10 years papers, you'll find a few times the definition of lattice has been considered as a 2-mark definition question. So what is a lattice? A lattice is a highly structured, ordered, microscopic arrangement. And let me tell you, this is a three-dimensional arrangement, and it is usually produced in solids when solids are present in the form of regular crystal structures, right? So what can you see in the diagram given above? Let's move a little. Take a look at this diagram. You'd notice that this diagram is three-dimensional: height, weight, and length. And you'd notice the particles are present in exact layers from top to bottom or from left to right. So this is the highly structured order arrangement that they were talking about. Three-dimensional because it has both length, width, and height. So I hope now you get the definition of the lattice. Do you?
Yes, sir.
Moving on. Liquids and gases both have the ability to flow. That's because the particles can move past one another. The space between the particles is also known as intermolecular space. We also sometimes abbreviate it as IMS. And in case of gases, the space is larger than a liquid. However, this case space can be reduced by increasing the external pressure. So we say the gases are compressible. This is one of the only places in the book, in this portion, Kinetic Model of Matter, where they discuss the compressibility of the gases. And liquid space is very much smaller, so liquids are not very compressible. Solids are not compressible at all. They are already present in a compressed state. All right. Any questions from this comparison?
No, sir. It's clear.
Good, great. Let's keep moving on. Next up is something that we have already studied. They have considered an entire heating curve so that with the passage of time, a solid is melted into a liquid and a liquid is boiled into a gas. And that's how one state of matter converts into another and then move on forward, keep the temperature going high, and you are able to convert it into gaseous phase. I hope we have clearly discussed that how one state of matter converts into other, what does melting mean, what does boiling mean, and how sometimes the states coexist too. Do we?
Yes, sir.
Good. This also discusses that sometimes the processes give out energy, sometimes the processes take in energy. The processes that give out energy are exothermic processes. Condensation and freezing are exothermic processes. The system itself cools down by giving out their energy. However, endothermic means a process that takes in energy. Melting, evaporation, boiling are all endothermic processes since they take in energy and then they bring about the change. Which brings us to our very next and another important topic of chapter number 1, that is diffusion. Diffusion actually happens in both fluids, which means liquids and gases. So let's go with the definition and some examples of diffusion. Before I start off with the examples of diffusion, can you define diffusion for me?
Yes, it is the process in which the um uh, the particles move from region of higher concentration to the region of lower concentration.
Good, good, great. This is the most common definition that students come up with. The diffusion is the movement of particles from higher concentration to lower concentration. That's very good. But let me tell you, at the level of O levels, we consider it as an incomplete definition. Now, at the very next page, before I start off with the example, I intentionally move to the next page. And on the next page, you're going to find key definitions. I'm going to go through the key definition. I'm also going to tell you what you are supposed to write if the definition comes as a part of exam. Now, this definition usually comes for 2 marks. Diffusion is the movement of particles. This is from a region of higher concentration towards lower concentration. This gives you 1 mark. And you must mention that the particles are evenly spread or evenly spread throughout the structure, and that would give you the other mark or the second and final mark. So this part of the definition is that the particles are evenly spread throughout the structure is also important along with the movement starting from higher to lower concentration. Make sense?
Yes, sir.
Good, good. Then they also tell us that it does not take place in solids and only takes place in fluids, that means liquids and gases. They also tell us that diffusion in liquid is much slower than the diffusion in gases, since the speed of particles for gases is much better than that of liquid, right? Let's take a few examples to explain the same thing. The first example that book comes up with is a potassium manganate crystal that is placed at the bottom of a dish, and they discuss what happens to it after a few minutes and after a couple of hours. Usually, you might have seen this example in the past papers. They ask you three types of questions. What would happen at the start of the experiment? What would happen after a few minutes? They might ask you after 10 minutes or 15 minutes. And what would happen after a couple of hours? For example, they might ask you about what would happen after 2 hours or 3 hours, or maybe 4 or 6 hours. They can ask you anything like that. Now, at the start, the crystal settles down at the bottom, being heavier than water, and the color slowly starts to spread. That's the start. After 10 minutes, we can very easily observe that the color is trying to spread in the lower part of this solvent. After 2 hours, or after 4 hours, after 6 hours, after a longer duration of time, you would notice that the color has lightened a little and eventually completely spread, evenly spread throughout the system. So that's when we can say when the diffusion is complete for this entire portion. Make sense?
Yes, sir.
Good. Since the diffusion in fluids is slow, the diffusion in gases is much faster. The bromine experiment in gas jars is a very easy experiment at that. Take a gas jar, the lower one that is filled with bromine vapors, and take another gas jar and invert it on top of this one. One is filled with bromine, and that is at the bottom. The other one is filled with air, and that is present at the top. You can place a card in between so the gases don't diffuse into one another, and you can take the card right out when you want to start the experiment. Otherwise, you do not need to put exactly a card or the lid. You can simply invert one gas jar on top of another, and the experiment starts then and there. Again, in this case, they may ask you what happens in the start, what happens after 10 minutes, what happens after 30 minutes. They're never going to ask about this experiment after a few hours because gases diffuse much more quickly than liquids. So it's not a matter of few hours, it's a matter of few minutes before the whole experiment is complete. And you might be able to notice that the whole experiment completes in 20 to 40 minutes. It does not require a few hours. So at the start, what happens is that we see a little bit of color moving towards the upper gas jar or the inverted gas jar. After a few minutes, we would be able to see color reaching the mid of the top gas jar. After some time, after 30 minutes to 1 hour, we would see that the color is evenly spread throughout. But still, we'll see some darker portion at the bottom since bromine is heavier than air, so most of it would like to stay and settle down at the bottom. Well, this is something for higher classes, since you'll get to know about the masses of gases in higher chapters. Not higher classes, higher chapters, upcoming chapters, I mean. Make sense?
Yes, sir.
Great. Moving on, we have another experiment. Now, before I explain this experiment, let me know, are you done with chapters like chapter 3 and chapter 5 or chapter 6 of this book in your class? In your class, in
Um,
your school?
let, let me
Chapter
check.
3 means the periodic table chapter, the chapter that consists of the bonding portion. And by chapter 5, I mean acids and bases chapter or salts chapter. By chapter 6, I mean the moles chapter, the stoichiometry chapter. So are you done with those chapters in the class? Or any of those chapters?
Yes, sir, we did chapter 3, like in pilot class. Like not in grade 9, I think in grade 8.
Yeah, I'm talking about the previous grades. I can totally understand that. Good. If you're done with chapter 3, that I'm going to come up with a few important things in this diagram, and hopefully you can understand this. When we're going with this diagram at the very start of the book, the teachers tend not to explain anything apart from diffusion related to this experiment. But since now we know, I'm going to explain a few more steps related to this one. Now, the experiment is pretty simple. We take a glass tube. At both ends, we have cotton wool soaked in different solutions. One of them has been soaked into ammonia solution. And let me clarify, this is the thing I was talking about. I'm going to write the formula of ammonia that is easier for you to understand what I'm going to discuss over here. On the other end, the cotton wool is soaked into a hydrochloric acid, the formula for which is HCl. Now, of course, I hope that you understand from chapter number 5 that these both can react together and can form a salt-like white smoke of ammonium chloride, NH4Cl, which actually appears over here. So this is that white smoke, ammonium chloride. Don't forget, ammonium chloride was the example that we discussed for sublimation in the very start of this chapter as well. I hope you remember that. Okay. So
Yes.
when these two gases combine, they chemically react and they form ammonium chloride, which appears as white smoke. And as soon as the white smoke appears, we can easily observe it even by standing outside and looking at this gas-phase structure. And we'd know that both the gases have traveled to a common point where they started reacting and forming a product. Now, what I'm going to do is that I'm going to put a little bit of scaling here. So this gets started traveling from this point all the way to this point. Let's say this is the center point, and this gets started traveling from this point to this point. Now you'd notice that a smaller distance has been covered by HCl and a much larger distance has been covered by ammonia. When I was talking about that, whether you're done with the most chapter or chapter number 3 or not, you'd notice that the mass of nitrogen is 14, that of hydrogen is 1. We're going to multiply it by 3 atoms since there are 3 atoms in the structure, and the total of this is 17 in terms of its mass. When I talk about HCl, I hope you remember from the periodic table, hydrogen is 1, where chlorine has the relative atomic mass of 35.5. Addition of what gives us 36.5 is the final answer. From these two values, you get a pretty good idea which gas has less mass and which gas has more. Since hydrogen chloride gas is more than double of the mass of ammonia, so you can clearly see being heavy, it covered less distance. And ammonia, being lighter, covered more distance. And we're going to summarize this point as I'm going to move a little bit. I'm not going to erase all of this. I'm just going to move to the next page so that I can target the summary point that we are about to discuss. So there are 3 very important points derived from kinetic theory which are relevant to diffusion. Number 1, heavier particles move slowly than the lighter particles at the same temperature. In other words, larger molecules diffuse slowly than the smaller ones. So this clearly gives us an idea, whether we know about it or not previously, this easily gives us a very clear idea about HCl, that HCl must be something heavier. If it was heavier, only then it was capable of traveling a shorter distance. And this also tells us at the same time about ammonia, that ammonia was lighter. That's why it was capable of covering almost double the distance than that of HCl. Fair enough.
Yes, sir.
I usually come up with a funny statement. I don't know which part of statement you're going to like or dislike, but मैं क्लास में उन बच्चों के सामने कहता हूँ मोटे लोग स्लो भागते हैं और पतले लोग तेज भागते हैं. So I'm not racist, but to give a funny example to make the students remember the point is that heavier particles, of course, are going to have a slower speed of diffusion, and
Yes,
lighter
sir.
particles, being lighter, will have a faster speed of diffusion. And it's the same thing that you observed in this very experiment. Even if a similar experiment is placed in front of you, and in exams, you're not familiar with the compounds given over here and here, does not matter. You should be able to answer that whichever compound, whether you're familiar with it already or not, covered less distance must be heavier or having a larger molecular structure, and the one that covered more distance, whether you're familiar with the molecule or not, is probably lighter or having a smaller structural size. That's why it was capable of covering more distance. Make sense?
Yes, sir.
So even if they come up with a totally unseen example with difficult names, with scary formulas, don't worry. You can always tell from the distance covered which one is heavier and which one's lighter. There are no exceptions to this rule. This rule is pretty strict, all right? At your level at least. So the heavier ones will always move slowly and the lighter ones will always move faster. Okay? Now I'm gonna, without my bad, without erasing the whole thing, I'm gonna again move forward and discuss the second point with you. On the next page, we have the second point derived from kinetic theory. It says the pressure of a gas is the result of collisions of fast-moving wall particles with the wall of the container. So if these two gases are in actually putting any pressure, that's because the particles of ammonia are capable of striking the wall of the container as well as other particles of ammonia. But the pressure is not taken its collision with other particles. The pressure is considered when it strikes the wall of the container. Make sense?
Yes, sir.
Remember, in this case, ammonia is just an example. The same thing is being done by the particles of HCl. They are also trying to collide the wall of the container and exerting pressure on it. So this explains the second point. If you're clear with it, let's move on to the third and last point, shall we?
Yes, sir.
Okay, moving on to the third and last point again on the next page, page number 40, you'd see that the average speed of the particles would increase with an increase in temperature. So how would this whole thing affect the same experiment? What if I started heating up this glass tube equally on all the ends? I started heating up it over here, starting heating up it over here, over here, over here, five same points. I started heating up the whole tube. Since it's a long tube, heating it up at one point won't bring a difference. Heating it up at multiple points will definitely bring a difference. What would happen to the experiment? Would any of the gases be able to cover a larger distance than anticipated, or what else? Your call. So, how would you answer this question?
Sir, could you please repeat the question?
If I start heating the whole gas tube at multiple points, what would happen to our observations in case of this diffusion experiment? Would there be any change? If yes, what would be the change?
Um,
Don't forget my point, and I'm going to scroll it for you again so that you can see the point and then discuss. Remember, the average speed of particles increase with an increase in temperature. So when I increase the temperature by heating it, the average speed of the particles inside the tube would increase. So how would it bring a difference to this entire scenario?
the speed will increase.
The speed will improve for whom? Are we talking about ammonia? Are we talking about HCl? Are we talking about air? Are we talking about both? What are we talking about? You need to be very specific with your answers. Go ahead and be a little specific with your answers.
Um,
Okay, let me ask you a few questions and you can simply answer them as you understand these, whatever your concept may be. Would the speed of particles ammonia increase more than that of HCl?
yes, because the HCl is heavier than ammonia, so HCl will move slowly and ammonia will move faster.
I'm not going to comment the answer. Instead, I have another question for you. The second question is that does it affect the speed of movement for HCl? As you just said that it is definitely going to affect the speed of motion for ammonia particles. So my next question is, does it affect the speed of or motion for HCl particles?
Yes, because the temperature is increasing.
Okay, good. So you are trying to say that the speed of both the particles, ammonia and HCl, have been increased because of the increase in temperature. Is that right?
Yes.
Good. Then what's the overall difference brought about by the increase of temperature to this entire experiment? Because the speed of both the particles will increase because of the increase in temperature, there would definitely be a change in this experiment. What would be the change? Can you be a little more specific about the answer? Or if you're confused, do you want me to answer? Whatever. You're called to pick
Sir,
the answer choice. All right. Let me tell you that the speeds for ammonia and HCl will both increase, and you're very much right about this. What would happen to the whole experiment? The entire experiment would just occur a little earlier in time. For example, if previously 10 minutes was taken for the white smoke to appear, this time it would only take 5 minutes or less. It's not about the distance. The distances covered by ammonia and HCl will not change by the increase in temperature. The position of white smoke will also not change by the increase in temperature, but it's just that the white smoke will appear a little earlier. If previously it was appearing after 10 minutes, it may appear after 7 or 5 minutes only. Makes sense? So the entire thing happens a little earlier in time, a quicker way to establish the whole experiment. Makes sense?
yes, sir.
Great, great. So keep in mind the temperature is not going to affect any individual speed than the other. So the distances traveled by ammonia and HCl will not be catered by temperature, since we are actually increasing the temperature equally for the whole tube. If we were favoring one side than the other, of course, the results would have been different. Since we're not favoring any of the sides, the overall experiment is going to occur a little earlier in time than anticipated. So this is how we explain all 3 points that are derived from kinetic particles theory and that relate with diffusion. Make sense?
Yes, sir.
Okay, good. Let's move on. Next up is the Brownian motion. Brown was a scientist who discussed this motion, and he actually had a small glass cell filled with smoke. Light is shown through the cell. The smoke is viewed under through a microscope. So he has light on it, he has the smoke, and it goes through the small glass cell. And he saw the smoke particles consistently moving. Not just moving, they kept on changing their directions. So Brownian was the person who confirmed us the random motion in particles. As you can see, this particle keeps on changing its own direction by colliding with other particles like itself or by colliding with the particles of air. So now you understand what random motion seems like. Makes sense?
Yes, sir.
So if you need a proof for random motion, Brownian motion is a great proof to tell that random motion is possible, and Dr. Robert Brown actually saw it too. Okay? All right. I would specifically like
Yes, sir.
to solve for you to solve question number 2.15 at the bottom of page number 40. The question states, which gas will diffuse fastest of all?
What question?
Question number 2.15, this one beta. Which gas will diffuse fastest of all? This also has been a past paper MCQ.
Um, It will be hydrogen.
Why? That's correct. Why?
Because it has like the lightest weight, so that's why it will diffuse fastest.
Because it's the lightest gas, it can diffuse the fastest. Well done. Hydrogen gas is the lightest gas of the planet, and of course, it would be the fastest of all. Easy enough?
Yes, sir.
Okay, good, good. Let's move on. Right?